So the key idea is that instead of scaling up the number of ports per router, we're going to scale out the topology through what's called a multi-stage switched network. This is a network with many switches. For example, a simple 2x2 switch, 2 input, 2 output, can be either configured like this or can be configured like that. So there are only 2 possible configurations for this small 2x2 switch. And if we connect many of these kind of switches, which could be 2x2 or larger, 2x3, 3x2, 4x4, then we form a network of connectivity determined by the configuration inside each switch. If this runs through multiple stages, we call that a multi-stage switch network. It turns out that you can build a large network using only small switches, but many of them, and arranged in a smart way across multiple stages. And that's what we mean by scaling out the topology to enable the scaling of the network, even though we do not scale up the number of ports for each network element. So here's a simple example to illustrate that. We got on the left the exact kind of tree that we just drew. You've got 8 servers as leaf nodes in circles, and you've got switches and rectangles, starting from small switches, 2x2, going to 4x4, going to 8x8. Okay, so suppose, let's say that we don't want switches larger than 2x2. So this layer of switch is still okay in the tree, but this and this layer is not. So one possibility is to replace each of these 4x4 switches with 2 2x2 switches. So one 4x4 somehow is equivalent now to 2 2x2. For example, this is a 2x2, this is another 2x2. I put the two together, and now the lower layer switch will actually go talk to each of these switches, and that collectively function as this 4x4 switch. By symmetry is identical on the right hand side. And then the uppermost layer for this small example is an 8x8 switch, and we'll show that it can be done equivalently as 4 2x2 switches. Okay. Each of these is a 2x2 switch, and then each of them is connected, one linked to the left half, another to the right half. Collectively, these 4 act as an 8x8 switch. And by the way, each one is indeed 2x2, even though you only see 2 links here, because 2 links need to come in and then they also need to go out. Right? So this is just an artifact, a visual artifact created by folding these switches. We'll look at an example of this again. But each of these is a 2x2 switch. So now if you look at this, instead of having altogether 7 switches, but some are big switches, and we now have a collection of 12 switches. So we almost doubled in this small example the number of switches, but each switch is only 2x2 now. Okay, instead of scaling up the port count per switch, we scale out the topology of connectivity pattern. We will look at a special case called the cloche network of such connectivity pattern, invented by Cloche in 1953. But in general, there are so many choices, and they are studied in the field of interconnection network, which has been studied in different application contexts, starting with 1950s and 60s in actually circuit switch networks. Even in telephone network, PSTN, people realized by then that, hey, you cannot build a large enough mechanical or electronic switch. So you need to scale out the topology with multi-stage switch network. Then was studied in parallel computation in the 60s, 70s to 80s, okay, with many mainframe computers connected together into a supercomputer. Then the scale got shrunken to a much smaller one. We're looking at systems on a chip and multi-core processor in the 90s and the last decade. And then in recent years, revived again in the context of data center networking, connecting servers within a large data center. All these are different cases of interconnection network. And the common theme is that connectivity pattern is a resource you have to carefully design. And there are many different metrics to compare different kinds of interconnection networks. We'll mention two. One is called bisection bandwidth. The other is called blocking or non-blocking property. Now, the idea of a bisection bandwidth has to go back to a simple graph theoretic operation called a cut. So suppose you're given a graph G, which is really a set of nodes V, a set of links E. A cut is to say that I'm going to divide this node set into two parts, V1 and V2, which equals to the original set of V minus the set of nodes in V1. Okay. And a bisection is basically a binary cut where the two subsets are of equal number of nodes. For example, here would be a network with a bisection this way. Okay, so I divided the total set of nodes into V1 and V2. Now, what about the links? Some links are entirely inside your V1 or V2, connecting only nodes all in V1, all in V2. Then those links are just fine. What about the links that actually connects across V1 and V2, like these three links? Well, we can count them if it's an unweighted graph. Or if it is weighted, we can add up their weights, like 2, 3, 5. All right. Then we add them up, and this is called the capacity of that cut. Okay. The capacity of a cut, in this case 10. In general, it is some real number representing the sum of the links connecting across the two sides. In the case of a bisection, two equal parts, then we can say it's the capacity of that bisection. Now, there are many ways to cut the given graph into two parts or two equal parts. For example, this will be another cut. Okay. Now, these two nodes belong to one side, these two belong to another side. So you can look at all the possible ways to cut or bisect and then find out the minimum one. Okay, the one with the smallest capacity, that's called the minimum cut. And the resulting capacity, in the case of a bisection, two equal parts, is called the bisection bandwidth. It's the worst case connectivity between two equal parts of a network. Okay. For example, this cut, let's say these two links cut weights 1 and 4, then this weight of cut gives you a capacity of 8. This weight of cut gives a capacity of 10, as we just saw. 8 is smaller than 10, so the minimum cut is this, or minimum bisection in this case, and the bisection bandwidth is 8 units. Now, there's also a famous theorem connecting the mean cut with the amount of flow you can squeeze from one node to another. Let's say you want to squeeze a lot of flows from the source to this destination through this graph. Okay. For example, I want to squeeze, say, 30. Well, 30 is impossible because there are only 16 plus 13, 29 units that's available to come out of the source. So let's say, all right, I want to squeeze 29 then, all right? And split 16 out of 16 go out this way, 13 out of 13 go out this way. So both links of capacity are fully utilized, all right? Then what? The 13 arrives here, it can go out. Okay, either part of this along this link with capacity 4 or along this link with capacity 14. It can all go along this link, for example. Now the problem is 16 units arrive here and there's only one way to go out. That way has a link with capacity only 12, which is smaller than 16. So you cannot squeeze all 16 units out of this node. So 29 is not a flow that you can squeeze through from the source to that destination. So now the question is, what is the maximum amount of flow that you can squeeze from source to destination for this given topology and weights or capacity on the links? Well, that is the famous maximum flow problem, and there are several very famous efficient algorithms to solve that. Now, this is not a graph theory course, so we won't go through all of them, but I want to highlight one very elegant theorem that says the following. Well, if you want to find out the maximum flow through the network between 2 points, it's the same as finding the minimum cut where the source lies on one side of the cut and destination on the other. So source belongs to V1, the subset of nodes, and destination belongs to V2, another subset of nodes. It turns out that this shaded configuration is the cut with the smallest capacity, that is the min cut. Okay, you can convince this yourself by cutting in different other ways. In this min cut, we see that going from the V1 side to the V2 side, there are 3 links of capacity 12, 7, and 4. So you add up together, that is 23 units. So the min cut capacity for this graph, where source and destination lies on 2 different sides of the cut, is 23 units. So is it indeed possible to actually push 23 units from source to destination? Yes, and here's one way to do it. You put 11 on this link, 12 on this link. How do we get this split into 11 and 12 this way? That can be discovered by those graph theoretic algorithms that we're skipping. But now, once you get to 11 here, that's fine. 11 can all go on this way. 12 comes here. 11 will go here, and 1 will go this way. So altogether got 1 plus 11, 12 units that fully utilize this link. Okay. This link is not used, and the 11 arrives here. You can split into 4 and 7. Now you see why we took 1 unit off this way. Because if all 12 unit gets to here, then you won't be able to put them onto these 2 links. So it's not a surprise. And in fact, for a small example, you can eyeball that indeed you should put 1 out there. And then the 1 together with 11 will saturate this link, and the 11 will be able to saturate these 2 links. And then once the 7 arrives here with 12, it adds up to 19, but it can be supported out of this link with unit of 20 capacity. So now finally this destination gets 2 things coming in, 1 with 19, 1 with 4, so all 23 units are received as they were transmitted out of the source. So indeed, as you can verify yourself, there's no way to increase the flow from source to destination. So the maximum flow is 23 units, which is the same as the minimum cut size. So that's a long detour of a fun, important classical result. But in data center design, when you scale out the topology, you want a large bisection bandwidth, okay? A large potential bottleneck to the performance of communication within the data center. The second criteria we use is called non-blocking. It originated from the circuit switching world for the telephone network. There's something called non-blocking and something called rearrangeably non-blocking. Non-blocking says that for whatever traffic pattern arrives in the multi-stage network, which we're going to draw momentarily, as long as this input port and that output ports themselves are available, you should be able to find a way to pass it through this multi-stage switched network. So the connectivity pattern should be able to support that. And rearrangeably non-blocking is a weaker condition that says, well, you may not be able to do that, but if I allow you to rearrange some of the existing connectivity patterns. For example, instead of going this way, you say, well, you should go this way. And this opens up a way for this input to go to this output. As long as you can rearrange existing configuration and then be able to achieve non-blocking, then that's also good. Okay, so this is a weaker condition. Now, what kind of switch network will have blocking or rearrangeably non-blocking property? Well, only those that have rich enough connectivity patterns in them. And indeed, in 1953, Klosch invented a particular connectivity pattern, and we're going to see the kind of non-blocking conditions on the parameters for such networks.